Hello, I'm Zachary Pringle, and this is my workshop 3. This project is going to focus mainly on the 4 different centrality measures of stress, betweenness, closeness, and graph centrality. The first part of this project that we're looking at has to do with motorists and using their GPS to find the shortest path from one city to another. The goal in the end is to find an ideal location to put a gas station that falls on these paths. Um, I decided to use betweenness to find the ideal location to put the gas station, and I chose this because betweenness gives you the highest ratio of traffic that's traveling through it, so the most amount of traffic based on the shortest path. Um, since betweenness is the total number of shortest paths that travel through a vertex over the total number of shortest paths. So the ideal location would be able to put the gas station where the highest betweenness number or the highest betweenness value is set. So here's a visual example of the motorist problem that we looked at in the last slide. So in this case, we're looking at motorists traveling from city 1 to city 6, and we want to find the highest betweenness value for a vertex between city 1 and city 6 to put our gas station. So the ideal locations is to either put the gas station on city 2 or city 4 in this case. City 2 is because there's 2 shortest paths. Along with city 4, there's also 2 shortest paths. So the shortest paths for city 2 would be from city 1 to city 2 to city 3 to city 6, and from city 1 to city 2 to city 4 and to city 6. The shortest path that would involve city 4 would be from city 1 to city 2 to city 4 to city 6, and from city 1 to city 5 to city 4 to city 6. That would mean there would be 2 out of the 3 shortest paths running through both of those vertexes, meaning those would be the 2 most ideal locations to put the gas station. So we're going to start off by looking at stress centrality and how to calculate this. Stress centrality is the measure of the number of times a shortest path runs through a specific node. So in this case, we're going to look at traveling from node 0 to node 5. The shortest path that can be possible out of this is 3, 3 edges to get from 0 to 5. And the stress when looking at, let's say, the purple node, node 3, would be 2, since there are 2 shortest paths that travel through this. Those shortest paths would be 0, 1, 3, 5, and 0, 4, 3, 5. Finding the betweenness measure is similar to finding the stress measure, and we did talk about this a little bit in the motorist example, but betweenness is the measure of the total number of shortest paths that travel through a specific vertex over the total number of shortest paths in general. So again, if we're looking at traveling from node 0 to node 5, there are 3 total shortest paths that there are from 0 to 5, and that's 0, 1, 3, 5, 0, 4, 3, 5, and 0, 1, 2, 5. And in this case, if we're looking at, again, node 3, the purple node, the betweenness would be 2 over 3, since 2 of the shortest paths travel through node 3, and there are 3 total shortest paths, so it's 2 over 3. Closeness centrality is a measure that checks to see how close a node is to all of the other nodes in the graph. The calculation for this is 1 over the total number of distance between the other nodes. So in this case, if we're going to look at node 3 again, the purple node, there is a distance of 1 between 3 and 1, a distance of 2 between 3 and 0, a distance of 1 between 3 and 4, a distance of 1 between 3 and 5, and a distance of 2 between 3 and 2. And this would mean that there's a total sum of 7. So the closeness centrality number would be 1 over 7, which is equal to 0.143. Graph centrality has the same type of idea behind it that closeness centrality does, but in this case it looks at the farthest node away from the node that you're looking at, and it does 1 over the farthest node away. So in this case, if we want to look at, again, node 3, the farthest node away would be 2 edges away, so it would be 1 over 2 would be your measure of your graph centrality. Alright, so this is going to be my problem that I am solving. I'm going to solve for stress in betweenness, and I'm going to show you some code for it. I actually found the code on the site that I'm going to put in citation at the end, and added the stress and betweenness values into it, since technically that code just spit out all of the shortest paths. So it's pretty easy to take all the shortest paths and find out which ones run through a specific node, and then do that node, all the stress on that node over the total number of shortest paths to find our betweenness value. So in this, you'll see the overall time complexity and space complexity in the next few slides. Alright, so we're going to look at solving this problem for the stress in betweenness. Again, this is the graph we're using for the problem, and here's our code. This is our main part of our code right here, and we're just setting the number of vertices to 5 in this case, since we have 0 through 4. Then we are setting a vector that holds the adjacent list of pairs of lists, Then we have our edges that we're adding, and I'll show you the function of the add edge at the top. And then we are setting our values down here for our source value, which is 0, which is our starting node, our destination value, which is the total number minus 1, since we start at 0, so we have 5 minus 1, so our destination will be 4 that we're trying to get to from 0 to 4. And we're setting a stress value to, this is our just setting it to 0. This will be incremented every time one runs through a specific vertice. The S node is the node that we're checking the stress in betweenness on, and then we're also going to set a value of betweenness to 0. This will be incremented to tell us the betweenness value, and then we want to print paths. This will just show the paths for all of the shortest paths that exist, and we'll also show you that function coming up. Alright, now we're going to look at this add edge function that we have here. It's going to have this vector being passed into it, which holds 5 different values. It's going to look at the edge from 0 to 1, the edge from 0 to 2, the edge from 1 to 3, the edge from 2 to 3, and the edge from 3 to 4, which will help us get our paths. So if we come up here to the function, we have our add edge function taking the vector, the source, which is just the starting vertice that we're on, and the destination is the end vertice of the edge, so like the start of the edge and the end of the edge. So then we add in, we push the destination onto the back of the source node, so we know that there's a path to that in this vector. So once we have our edges added in, it'll do this print paths function, which will call some of our other functions as well. So if we go up to our print path function, we're taking in our vector, our int of n, which is 5, our start value of 0, our end value of 4, our stress of 0, our s node of 3, and our betweenness value of 0. Then we're creating a new vector in here with another vector inside, which just makes a matrix, which will hold the paths for the different vertices. Then we'll have another vector that will hold a path, and then another vector that will be the parents for the different nodes that are in this graph. And then we're going to run our breadth first traverse function here, which takes in the vector here, the other vector here, the value of 5 for the amount of nodes, and then the start value of 0. So if we go up to this BF's function, it's right here with the vector, the parent, the n, and the start value. It's also going to create a new vector that measures distance and sends all the values to max, so it can look to see if it's smaller than a high, like a super high number kind of thing. And then we use Q to make sure we're not going backwards at all towards the node we just came from. So we have we push the start value in, which is a 0, into the queue. We set the parent start value, which is 0 here, equal to -1. So if it's the parent, it's the value of -1. Our distance of 0 is set to 0 to start, since it hasn't traveled anywhere. So then we run this while loop while the queue isn't empty, basically. So we set our u to the front of q, in this case it's 0, and then we pop off that value of q. So technically it's empty now, so if we got through this and went back to the top, it would be empty, but this gets added back in somewhere in here if it's not at the end yet. So then we run our for loop here that looks to see if the distance of v is greater than the distance of u plus 1. And if this is the case, it means we found a shorter distance between these nodes, like two nodes, so the new parent that gets inserted into the parent vector here, and that means that the node is a parent of the next node in line, basically. And then it'll also check to see if there's any other parents with the same value, and if there is, then it'll also push that parent into the parent vector for that specific node. So once we run our BF function there, we're going to start calling our find paths function, which takes in that paths vector, the path vector, the parent vector, the value of n, which was 5, and the end value, which will be the 4. That goes up to right here. There's taking all of our information in. So then if u is -1, which would be our parent, basically that just means it's our parent node. So if the place we're traveling is our parent, that's our best path we can take, so that just return right away. It's our best case. But if not, we have to run this for loop down here, which goes to the parent, and if it's not the parent, then I'll have to go to one of the parents and check to see if that path works. So then we're starting to create a path. It'll go to that next path, and it'll push back the next value or the next vertice into that path, and then it'll run the function again. So then if that parent is the parent of our last value that we're trying to get to, it returns it. But then if not, we would go back down to here, and we would put on our next parent, and then we do the same thing, and that would give us our path from the start node into the end node. So once we find the path, it's time to print the path out. So we run our for loop here, which the path is created in reverse order currently, so we have to reverse that order. So it just takes the vector and reverses it at the beginning and the end. It just now makes them opposite. Then we run this for loop inside of that, which just displays the value of u, which is just the path at that vertice of 0. So our path goes from, if we look back at our original problem, we have this path right here. So we want to go from 0, 1, 3, 4, and 0, 2, 3, 4. So those are the values that will start getting returned out of this. I also have something that checks to see if the value of u equals the start value, which was 0. Betweenus gets added in. It just means that anytime there is a new shortest path made, it adds 1 to the betweenus value. So that's how we are going to check the betweenus value. So we have our total number of nodes, total number of our shortest paths checked here, and then we're going to have a second if statement that adds a value to stress, and this is going to be the amount of shortest paths that run through the specific node we're looking at. In this case, it's 3, so S node is 3. So anytime a 3 comes up, 1 gets added to stress, and then we add in our cout statements here. So we have the stress is just the value of stress, since that's the amount of shortest paths that run through that node. And then we have another one that shows our betweenness, which is going to just be our stress value, and I times it by 1.0 here to turn it into something that can be divided and give us a decimal. But that's going to be our stress value, which is going to be, in this case, the 2, and over our betweenness value, which again in this case is also 2. So we just get 1 for our betweenness. So here's the output of the problem we had. Shows 0, 1, 3, 4. So 0, 1, 3, and 4 are our shortest path, and a 0, 2, 3, 4, 0 to 2, 3 to 4. Then we have our stress neutrality of vertex 3. So if we look at the purple node, when looking from 0 to 4 is equal to 2. So both of those shortest paths travel through the third node. And then our betweenness neutrality of vertex 3 is equal to 1 because it is our stress value, which is 2, over the total number of shortest paths, which is also 2 in this case. Alright, now we're going to look at our time complexity, which is this first column here. If we look at our main area here, we got a value being set, which is going to be a theta 1. Technically in this case, we don't know what n is yet, so we're going to just go down to our vector here, and it's going to be theta n, because n could be any size, but we want it to be. Then we're going to have our add edge function, and I calculate that as a theta 1, so if we go up here, all it's doing is pushing a value of those edges that we added in here. So those are theta 1 runtimes. Technically, however many edges you have would be a theta n total, but in this case it's running them one at a time, so it's just a theta 1. Each of these values being set here are all theta 1 values, and then we have a print path function that I calculated to have a theta n squared runtime. So if we go to our print paths function, we have theta 1 for all these vectors being set, because technically a vector isn't taking up space, it's added in as it goes. Then we have this, the BF function that runs, which the BF function is here. We have theta 1 for vector being set, we have Q being set to theta 1, theta 1 for the runtime on all of these, since there's no loops or anything yet. Now in our while loop, I have a theta n, because it's going to run n amount of times before that empties out. In this case, we have a for loop inside of a while loop, so it's going to run n amount of times inside of an n encapsulation, so it's n squared. These if statements could run up to theta n squared times, or big O n squared times, or also as little as 1, so mega 1, because if the if statement just doesn't run for all of these, it's possible that they don't ever get touched. And then this same with this parent down here, this parent value here. Then if we look back down to our paths function, we do our find path function. We'll go up to find path. We have a theta 1 value for this if statement. And then we have a for loop, so that's going to be our theta n. It's going to run until these values are set. They're all theta n since they're encapsulated within this for loop. So then we go back down to our paths function, and we're going to have a for loop here, which is going to be a theta n. It's going to run until all the paths are checked. Theta n since it's in the for loop, and then we'll have a for loop again inside of a for loop, which is going to run until this value of u is filled up, or until it's displayed, I guess, which is a theta n squared since it's a for loop inside of a for loop. These if statements only run if they're true. I guess the start one's always going to run in this case because u is always going to be included in there. So that takes us back down here. So our total for the print pass was theta n squared, meaning our total limiter on time complexity is a theta n squared. So now for space complexity, it's this second value here, and we're only running it anytime a new value is being set. So in this case, we have a value being set here, which is theta 1. A vector being set here, which is theta 1, since it's not taking up any extra space. Q here being set since it's not taking extra space until things are added in. So it doesn't actually dedicate space to it, it just gets added as it goes. Again, here we are setting this u value, which is just theta 1. Here we're setting our v, which is theta 1. Down here, set another vectors, which are all theta 1 values. And then we set our n value here, which is just theta 1. And then this vector here, we're going to call theta n because we don't actually know the size of n yet, but we know it has to be this at least size n. Then all of these initialized values are just going to be theta 1s. So the determining space complexity is just theta n, and that's all for space complexity. So again, when looking at our stress and betweenness value that we solved, we get an overall time complexity of theta n squared and an overall space complexity of theta n, while our stress value was 2 and our betweenness value was 1, which was just 2 over 2. So for part 4, we chose to do theorem 2, which looks at a vertex that can maximize stress centrality but doesn't necessarily maximize the betweenness centrality. So in this case, here's our starting graph over here on the right. And to start off, the stress on node 3 would be 2, and the betweenness would be 2 over 3, since there are 3 total shortest paths and 2 of them cross through node 3. And then we're going to add in our node n, which is our new node, and then these edges here. This now will increase the stress to node 3, since there are now 3 different shortest paths that run through node 3. But now there are a total of 5 different shortest paths that lead to node 5, meaning that the betweenness centrality is now only 3 over 5, since there's 3 that run through node 3. And 3 over 5 is a smaller number than 2 over 3, meaning there is a higher stress but a lower betweenness value. So here's a citation of where I got my code from. If you have any questions, please feel free to email me at pringlesy@umich.edu. Thank you for listening to my presentation.